Great, yeah, thank you for the introduction. And I also want to thank the organizers for giving me the chance to speak here. So everything I'll say is going to be joint work with two people, Chen and Christian Liedtke. And let me first give you a quick introduction to the kind of objects that I'm going to be talking about today. Namely K3 surfaces. So for me, as I guess for most people, I'm going to call a smooth projective surface X over an algebraically closed field K. I'm going to call such a thing a K3 surface if two things hold. First of all, the canonical divisor is trivial, and H1 of XOX is 0. Okay, so there's many examples of such surfaces, and many of them are kind of very classically studied objects. So let me give you a couple of examples. So the first example one encounters in nature is I just take an X inside P3, a smooth quartic surface. Okay, and such a thing, it comes with a natural polarization, namely the restriction of O of 1 from P3, whose self-intersection is 4, hence the quartic part, and this is a degree 4 K3. Okay, but these come, I mean, K3s, in fact, you can put them in countably infinitely many families, 19-dimensional families, as we'll see in a second, parameterized by their degree, and the degree is always an even number. So let me just give you one more example. If I take C inside P2, let's say a smooth sextic curve, and then I take X, the 2-to-1 cover, over P2, ramified along C. And here the natural polarization is, well, I just pull back O of 1 from P2, and the self-intersection will be 2 here, so this is a degree 2 K3. Okay, but as I said, I mean, if I give you any positive even integer, you can 2D, let's say, there exists a K3 surface with a polarization of that degree. Okay, so in fact, let me maybe now even fix the notation for their moduli spaces. So I'm going to call, I fix some d bigger than 0, and I call M2D the moduli space of 2D polarized K3 surfaces. Okay. And something that I'm going to be using over and over is that this space is in fact irreducible. Okay, I'm going to need one more moduli space, namely that of the lattice polarized K3s. And here I'm going to be a bit more loose about the precise definition and its global properties, but let's fix lambda a lattice, and then call M lambda, I guess, the space of K3's X, such that lambda sits inside primitively well, sits in the Picard group of X primitively, okay, up to isomorphism. So yeah, both of these spaces have very nice properties and have been studied by many people, including people in the audience. Right, okay, so these are the two modular spaces that I'm going to need. Right, so what problem am I going to be interested in on K3s? Well, it's going to be the existence of rational curves and in fact more generally of special curves on such surfaces. So this story goes back to Bogomolov and independently Mumford. And in fact it appeared in a paper of Mori and Mukai, but it's the following statement. Basically, if I have a K3 X, again over an algebraically closed field, then there exists a rational curve on X. Okay, so there exists an integral subvariety of X whose normalization is P1. Okay, so this is entirely kind of non-obvious just from the definition, right? I mean, here I've given you something about the numerical properties and something about the canonical divisor. So where would you construct this rational curve? So Bogomolov and Mumford did this by essentially degenerating to a very special K3 surface, namely a comma, which is the product of two special elliptic curves. And there they can construct a special configuration of rational curves and show that using the irreducibility of the moduli space, I can deform that curve out to the general K3 surface. So making that curve now irreducible. So every general K3 surface, namely for an open subset of the moduli space, every K3 contains at least one irreducible rational curve. And then when I have one, well, I just specialize my K3 to any K3 in the moduli space. And then that curve, I mean, it might break up, but it can only break up into rational curves. So certainly every K3 will have at least one rational curve. Okay, so this theorem is not very difficult in modern language, but I mean, you have to set up the notation using moduli space of stable maps, and you have to do the degeneration carefully, and it uses this irreducibility, so it's not entirely trivial, is my point. Okay, so in fact, this can be pushed to the following statement, that if I take D a non-zero effective class in the Picard group, then there exist Ri rational curves in X such that D is linearly equivalent to the sum of Ri. Okay, so possibly with multiplicities, this could be complicated. Okay, so at the moment, I mean, what I've written down says that anywhere that I look, in any effective class that I look on any K3 over an algebraically closed field, I can write that class as a sum of rational curves. But I mean, it's wholly possible that, first of all, you know, as I take multiples of D, all I'm doing is I'm just writing multiples of D as a multiple of the same rational curve, right? So those Ri's, they don't have to be distinct. I'm not making any claims of that kind. So at the moment, it could be that a K3 only contains one or just a very small finite number of rational curves. Okay, so one observation is that as the Kodaira dimension K of X is 0, if the field is in characteristic 0, then X is not covered by rational curves. i.e. it's not uniruled. So if these curves exist, they don't move inside X, right? I mean, there could be finitely many, there could be infinitely many, we don't know, but none of them will move. They won't sweep out the whole of X. So this fails in positive characteristic, but for the purpose of this talk, I'm going to kind of avoid supersingular K3s, even though for the purpose of the paper, we certainly don't, we have to work on supersingular K3s as well. Okay, so none of them move, but the conjecture, which I'm not entirely sure who to attribute to, but some people attribute it to Bogomolov in the 70s, is that if X over K bar a K3, then X has infinitely many rational curves. Right, so infinitely many distinct subvarieties of X whose normalization is P1. Okay, so this has a very rich history with many people, and let me give you kind of some of the important results in this direction. So perhaps the most important first case is that of Chen, namely the same Chen who's co-author on this paper. But it says that if, well, let me focus just on the case where K is C from now on. It says that if XH inside M2D is very general, i.e., so M2D is a irreducible space, we said, but after removing a possibly infinite countable union of closed subvarieties of M2D, then the leftover points I call very general. So such a K3 not only has infinitely many rational curves, but has infinitely many nodal rational curves. Okay, so this is way stronger than what we expected, right? I mean, in general, I have no control over the image of that Bogomolov-Mumford curve. It could be cuspidal, it could be, you know, as awful as you want. But on the very general member, we expect these to be, well, we know these to be nodal, sorry. And yeah, so this had many applications to counting problems. For example, the resolution of the Yau-Zaslow conjecture by Beauville. So Chen proves a second theorem, which basically says that if X, H is general in M2D, and H is a primitive polarization, then essentially every rational curve in H has to be nodal. So a priori, you know, some might be nodal, some might not be, but everything in the primitive polarization of a general K3 has to be nodal. And this means that if you've seen these Yau-Zaslow formulas, it's just saying that basically this number that Yau and Zaslow gives us in this generating series, it's actually counting nodal rational curves in the principal polarization. But that's a different side of the story. So I'm going to try to focus on whether there exists infinitely many on every K3 today. Okay, yeah?
Is there any statement about the degree of the rational curve? Can it be bounded?
By degree, you mean with respect to intersection with H? Well, here, on the very general one, he constructs them in multiples of H.
Yes, but it's infinite sequence.
Yes, but they're irreducible, right? So they're in H, they're in multiples of H, so you know that it goes to infinity, yeah. Right. Okay, so already I mean, I mentioned earlier that the way that you construct one rational curve is you find one on a general one, and then you specialize, and you know, it might break up, but you at least have one on every K3. So at this point, I mean, you might be wondering, well, if the very general one has tons of nodal ones even, then why can't I just specialize all these, since the moduli space is irreducible, to any given K3, and there get infinitely many rational curves? And this has been a kind of a problem for a while now, and let me just give it a name, and let me call it the specialization problem. Okay, and this is precisely, well, one kind of nightmare scenario is, well, I take a very general K3 which has infinitely many rational curves, I take one special K3, I put them in a family, these two, I start taking these infinitely many rational curves from the very general one and specializing them to my special K3, but it could be that every time I specialize, my rational curve splits up into sums and multiples of like a finite number of rational curves, maybe even multiples of one rational curve if it's Picard rank 1, let's say. So all these nodal rational curves could specialize to finitely many on an arbitrary K3. Okay, and this is the main problem that I'm going to have to deal with if I want to prove this conjecture. So let me give you quickly some other known cases. First, there's a paper by Bogomolov and Schinkel. So I should say Chen's result was in '99. It's his PhD thesis. This was roughly a year later, and they proved that if x, so conjecture is true, if x is either elliptic, namely in admits a morphism to P1, or if the automorphism group of x is infinite. Okay, and note here that if rho is the Picard rank of x, then rho is a number between 1 and 20. So again, I'm just talking about complex K3s now, right? And moreover, if rho is bigger than or equal to 5, then x is always elliptic. Okay, this is basically a lattice. Well, it's an arithmetic thing that one can prove. Okay, so the ones that we're left with are Picard rank 1 to 4. Right? We know the very general one, but this is not suffice to give the remaining cases. Okay, so other important cases were by Bogomolov, Hassett, and Tschinkel. And they proved the case where rho is 1 and 2d is 2. So this is a kind of a very specific case, right? I mean, as I said, the degree is a number that's could be, you know, it's a finite number, but it could be any even number. So they prove it in the case where rho is 1 and the degree is 2. So this is quite specific, but this paper is extremely influential in the area because the techniques they developed to deal with it are basically the techniques which ultimately will lead to the to proving this conjecture. Okay, and then leading on from Bogomolov, Hassett, and Tschinkel, there was a paper by Lee and Liedtke which essentially pushed their techniques almost to the extreme, and they prove that rho, so the conjecture is true when rho is congruent to 1 mod 2. Okay, so in particular you get the Picard rank 1 case, which really is the hardest case. So if I have some time, I'm going to tell you a tiny bit about this proof in a second, but let me kind of plow on. So what remains, in other words? Well, we know that if the Picard rank is at least 5, we're good, and we know that 1 and 3 are good because of this thing. So the only thing left is 2 and 4. So rho is equal to 2 or 4, and x not elliptic, and the automorphism group is finite. Okay, so this is where I guess we come in, and what we prove is the following theorem. So if x k3 over the complex numbers and A inside pick x ample, then, let me phrase it slightly differently, and take a G a non-negative integer, then there exists a sequence Cn of integral geometric genus G curves in X such that the limit of Cn dot A is infinity, as n goes to infinity. Okay, so in particular, if G is 0, this implies that the conjecture is true over C. Okay, so today I'm only really going to talk about rational curves, but let me give you kind of verbally a brief explanation why I have to phrase this theorem in this weird way. Namely, for rational curves, I can just say, well, every K3, the statement of this theorem is that every complex K3 has infinitely many rational curves. Okay? But for higher genus curves, the trick is that if I give you one integral geometric genus 1 curve on a K3, then this moves. Okay? So in fact, you can prove that every integral geometric genus G curve on a K3, it moves in a G-dimensional family in its linear system. So saying that a K3 has infinitely many genus 7 curves is a bit silly because having one suffices. Right? I can always move it. So what this is saying is that you can find infinitely many classes of divisors represented by geometric genus G curves. Okay, so in particular for rational curves it doesn't matter because none of them move, so they automatically have to be in different classes. But for higher genus curves you have to say that the classes are different. Okay, any questions so far about the statement? Okay, so let me give you a brief flavor of, well, okay, maybe first of all let me come out and say immediately that the proof of our theorem relies on the previously known cases. So just to be precise, what we do is we use Bogomolov Schinkel to deal with the Picard rank at least 5 and elliptic and infinite automorphism cases. Then we reprove using a technique that I'm going to sketch now, the Liedtke theorem, namely the odd rank case. And then we use results of Winberg and Nikulin to deal with to limit the rank 4 cases to only 2 precise lattices. And then we deal with those 2 precise rank 4 lattices and all of the infinitely many rank 2 lattices using something that I'll sketch at the end. Okay, so we certainly do use the previously known cases. Okay, so it's really a case-by-case analysis. Okay, but what I'm going to try to convince you is that, okay, we do prove this theorem, but ultimately what we do is we give 2 techniques to move integral geometric genus G curves around the moduli space, namely to pass them from the general one to the special one so that it doesn't break up like in the specialization problem, and conversely to start with a curve on the special one and move it to the general one. So some of this stuff has been known, but let me give you a brief sketch. So take X over S, a family of K3s, over a DVR. And I have to decorate here. I have to say that the DVR has algebraically closed special fiber. And in fact, I also allow mixed or equicharacteristic P, but let's not get into this at the moment. But okay, so there's 2 points here, namely 0 and eta, the generic and the special point respectively. But if you have such a family, then, well, it can be, well, we know that rho of the generic fiber is always less than or equal to rho of x eta, of x0. Okay, so when you specialize, the Picard rank could jump. And in fact, let me just give you one example, which is, I guess, instructional here, of where you get strict inequality. So if I take x eta inside P3, a very general quartic, this will have Picard rank 1. And then I take x0, a K3, well, a quartic, sorry, let me just call it what it is. A quartic containing a line. Okay, so a line will be a smooth P1, closed embedded in x0. Its self-intersection is -2, but it's effective, so it forces the Picard rank of x0 to be at least 2. So here I have a Picard rank 1 K3 specializing, let's say, to a rank 2 K3. And this curve, it cannot come from a curve in x eta, because if I could move this line, if I could deform it somehow to x eta, then there'd be a -2 curve on x eta, and that would contradict the fact that it's Picard rank 1. So what do I mean by being able to move curves around? Let me state it perhaps more precisely as a problem. So given C0 in x0 integral, can we deform it to x eta? Okay, and I've already given you an example where where you cannot do this. Okay, so the question is, how do I fix this? Well, the first is to add a condition, and this goes back to work of Rahn, Bloch, and also Clairvoisin. And it basically says that there is an answer to this problem, namely yes, if the class of this integral, namely the class of this curve in the Picard group, it lifts to the Picard group of x eta. So if O xO C0, CO lifts to pick x eta, then yes. Okay, and what I mean by this is, namely, there exists an integral curve of the same geometric genus as C0 contained inside x eta, which specializes to C0. Okay, so that's a precise statement that I'm making here. And the way that you prove this is, well, you do some dimension estimates on Hilbert schemes and ultimately the Conservitz moduli space of stable curves, and you use the twistor line. Or in positive or mixed characteristic, you use the formal deformation space. Okay, so I don't want to spend too much time on this. If you haven't seen it before, it's a beautiful technique. It works more generally for hyperkähler varieties and others, in fact. But basically, this existence of a symplectic form, I mean, it gives you this twistor line. This gives you an extra dimension to play around with in the Hilbert scheme. Okay, but as this example shows, I mean, the class of the line, it cannot lift, right? Because the class of the line is a -2 class, and there is no -2 effective classes in x eta on a very general quartic. So how can we move such a thing? So this I'm going to call theorem B. So if C0 in x0 is integral, and let me just say that x0 is not supersingular. Well, actually, no, sorry. Let me erase that and put a much simpler assumption. So x0 is in characteristic 0. And let me just say in parentheses that, in fact, also most cases in characteristic P, but I really don't want to get into this right now. It takes a while to kind of state everything. So if I have a family over dVr where the special fiber is in characteristic 0, and I start with an integral curve in the special fiber, then, well, I might not be able to move the curve itself, namely with its class, but after adding some rational curves to C0, then I can lift the class, and the whole curve moves. So how do I say this more precisely? Then there exists d eta inside, well, d inside x eta geometric generic, such that two things hold. First, the geometric genus of d and C0 agree. Right, that's an important thing. When I move curves, I want to preserve the geometric genus. And the second is that the specialization of d to x0 contains C0. Okay, so I call this regeneration. So I call D a regeneration of C0 because it's an inverse to specialization. Right? I mean, I might have to add some things to C0, but what I'm adding is just rational curves, so it's not that bad. Let's see. Okay, are there any questions about this? Let me maybe draw a picture. So I have my x eta, I have my x0. I start with a C0 here, integral, possibly singular, as bad as you want. Its class may not lift, but I can attach some rational curves, possibly cuspidal with multiplicities, I don't know. But now there will be a D which has class equal to the class of this entire sum. So that, yeah, and it's basically D, when you specialize it, you get this whole thing. Okay. So in particular, yeah, C0 is a component of the specialization of D to x0. Okay. All right, so an immediate corollary of this, well, there's two in fact. The first is if x0 has infinitely many rational curves, then so does x eta. Okay, so how does this work? Well, I take one rational curve in x0, I regenerate it, I get a rational curve on x eta. Then I take another rational curve on x0, I regenerate it, I get another rational curve on x eta, and I do this infinitely many times, and I produce infinitely many integral rational curves on x eta. Okay, so in particular what this says is that to prove the conjecture, you just have to find one specialization of your K3, which for example is elliptic. Because then we know that x0 has infinitely many rational curves by Bogomolov Schinkel, and you're done. And maybe one more corollary is that we reprove Lie and Liedtke, and the proof becomes kind of very quick and a bit more conceptual. Yeah.
Can you explain the first point again? As D perhaps has high genus when you specialize.
Sorry?
Isn't it possible that D has high genus, but it breaks when you specialize?
No, all of these are rational curves. So these are Ri, they're all rational curves. So the geometric genus of D will be the geometric genus of C0. Yeah, so I mean, geometric genus of a sum of curves is the sum of the geometric genera of the normalizations. This is really crucial. Otherwise, of course, if I was regenerating and getting genus 1 curves, then that's useless. Okay. Let's see, I have almost 15 minutes. Let me just say verbally 2 words about the proof of the second thing. I mean, I already told you the proof of the first thing. So the aim of the game becomes to find, so you start with a complex K3 and you want to show that it has infinitely many rational curves. So the aim of the game now becomes to find specializations of your K3 where the Picard rank at least jumps up. Right? Because if it jumps up, maybe you get lucky and it jumps up to 5 and then you're done. But let's say that you start with a K3 of Picard rank 1 and yeah, I mean, it could be that when you specialize it, it's still Picard rank 1, and then you have to somehow deal with proving that there's issues with basically showing that the degrees of the rational curves that you construct go to infinity. So ultimately the aim of the game now is to show that I can specialize so that the Picard rank jumps. So if your K3 is defined over a massive field, then, well, you can spread out over an irreducible base family, and then you have the existence of infinitely many Noether-Lefschetz loci. So you can specialize in infinitely many directions, and the Noether-Lefschetz loci are precisely the loci where the Picard rank jumps. So you can find infinitely many specializations where the Picard rank jumps, and then a Hilbert scheme trick shows you that every time it jumps, I can find a class there. I find a new effective class. I use this, maybe it's gone, this thing, the in fact part that came after the Bogomolov Mumford thing, that basically every effective class contains a rational curve. I take a rational curve in there that doesn't come from the Picard group of my initial X. I regenerate it, and then using a Hilbert scheme argument, I can show that if I specialize infinitely many times, I can make it so that I get infinitely many new rational curves on the generic fiber. Okay, so the deal is that it's often difficult to construct specializations where the Picard rank jumps. So in particular, what do you do if your field is small? Like, let's say your K3 is defined over Q bar. Well, then what you do is you spread out, so it's defined over some number field, you spread it out over the ring of integers. So now you have infinitely many prime numbers, and you can prove that for infinitely often you have good reduction. And now here comes the assumption of being of odd Picard rank. So I said that Lie and Liedtke, they prove their theorem assuming that the Picard rank is odd. Again, this is for a K3 defined over Q bar, let's say. So now there's this amazing application of both the Veil conjectures and the resolution of the Tate conjecture that says that if I have a K3 defined over FP bar, its Picard rank has to be even. This is not completely trivial. Well, obviously it uses the Tate conjecture and the Veil conjecture, but to explain it, I'll need a bit more time. But ultimately what I'm saying is that if I start with something over Q bar of Picard rank 1, when I specialize it to characteristic P, the Picard rank has to jump, because it can't be even. It has to be, sorry, it can't be odd, it has to be even. So if I start with Picard rank 1, it has to go to 2 or 4 or 6 and so on. So in particular, I always get a new class, and I can do this for the infinitely many primes, and then use the same Noether-Lefschetz type argument that I mentioned before with the Hilbert scheme argument, and show that you get infinitely many. Okay, but ultimately what you do is you regenerate for each prime, you get a new rational curve, you regenerate it, and then you show that all of these are distinct on X. Okay, so this at the moment, it leaves us with rank 2 and 4 cases that I said. Okay, so let me give you a sketch of the proof of theorem A in the genus 0 case. And to get higher genus, basically what you do is, well, you show it for genus 0, then you do everything again for genus 1. And by everything, I mean you prove Bogomolov Schinkel, namely this case that if the K3 is elliptic, then it has infinitely many classes of geometric integral genus 1 curves. And then you also prove the Liedtke theorem for genus 1 curves. And then when you have it for genus 0 and 1, you can basically attach these together into stable curves, and those stable curves have to deform to any higher genus that you want. And yeah, so basically this theorem reduces the proving for genus 0 and 1, and then basically we redo all of this case-by-case analysis for genus 1, and it's a lot of work, but it's very similar to the genus 0 case. So ultimately the genus 0 case is, let's say, the interesting thing to talk about today. Okay, so what goes into dealing with, let's say, the rank 2 case? It was the rank 4 case, as I mentioned, by lattice classification results of Wennberg and Nikulin. We know that there's precisely 2 lattices that we have to worry about, and we deal with those in a very similar way that we deal with the rank 2 lattices. Okay, so first we prove theorem T, where T stands for technical. And this says the following. So bear with me, it's a bit of a mouthful, but it says that if lambda is a lattice with this intersection pairing, so I need the Hodge index condition, which is that 4 dB minus a squared is less than 0. Okay, so I start with an arbitrary K3 lattice of rank 2. Okay, it always has to be even, and then A is some integer. And I take L inside lambda, big enough, which is positive enough. And by this I mean that I can write L as the sum of 3 other big enough guys, for example. Okay, it could be 3 times another guy, or it could be the sum of 3 other ones. This is, I need some kind of positivity of L. Then there exists a dense open UL contained inside M lambda. Right, so this is the moduli space of lambda polarized K3 surfaces. So the very general member will have Picard group isomorphic to this one in here. And in fact, we know probably by work of Bourvil, that this space is also reducible, but let me not get into that. Okay, so there exists a dense open depending on L, such that for every x inside UL, there exists a nodal rational curve integral in the linear system L. Okay, and let me contrast this with the important case of Chen. So essentially, this is a complete analog of Chen's result, but Chen proved it in Picard rank 1. Okay, and here we have to basically prove that if I fix a rank 2 lattice, then general members of that lattice will have tons and tons of nodal integral rational curves, right? So any big NF class, more or less, that I pick will contain a nodal rational curve for the general member. Okay, and I say this is technical. I mean, it takes more than 40 pages, I think. And essentially, you use it's the same type of proof as in Chen's original result, namely you degenerate to a log K3, which is singular, the union of 2 rational surfaces, and there you construct these special configurations of rational curves, and then you deform them out to the general member. But the difficulty is that we have to deal with special cases depending on whether the discriminant of this lattice is even or odd, and basically it's kind of a nightmare case-by-case analysis where you sometimes you degenerate to the blow-up of P2 you degenerate to the union of P2 blown up in 5 points, union some Hirzebruch surface blown up in some points, and if the discriminant is odd, you do a different degeneration, and then you have to kind of make sure that the specialized, these limiting rational curves that you construct, they lie in the right class, and all of this is kind of a technical analysis, which is case by case, but very much in the same vein as Chen's result. Okay, so already you see here that we want to prove that every K3 surface of rank 2 has infinitely many rational curves, but what we've proven is that, well, if I fix a rank 2 lattice, then the general member has infinitely many nodal rational curves. But again, we have the specialization problem. So when I specialize to an arbitrary rank 2 K3, it could be that all of these nodal rational curves, they become kind of sums and multiples of a finite number. And this is the problem that the next theorem solves. And yeah, essentially what this theorem says is that you can make it so that this doesn't happen. But I have to write this down a bit more precisely. Let X be K3 with rho of X is 2 and lattice lambda, and take L in lambda primitive. Now primitive, before I didn't make any assumptions about primitivity. Ample, which is positive enough. In the same sense as here, maybe it's a sum of 3 big enough classes, let's say. Then, the specialization of the nodal rational curve in L from theorem T remains integral. Right? So in other words, it doesn't break up into the sum of other things. And here I'm really using the fact that L is assumed primitive, but of course if my K3 is if it's rank 2, then there's infinitely many primitive classes. So for each primitive, ample, positive enough class, I find a nodal rational curve on the general K3 in that class, and then I specialize it back to my arbitrary K3 that I want, and it remains integral because of this theorem. Okay, so ultimately this proves the theorem in the rank 2 case. And then as I said, the rank 4 case, there's precisely 2 lattices that we have to worry about, and those we do a similar degeneration to the one needed for theorem T, and we embed those in some kind of rank 8 lattices and degenerate those rank K3s of those rank 8 lattices to, again, unions of rational surfaces and find tons and tons of nodal rational curves in essentially every class that you want for those rank 4 lattices, and then we prove theorem C, an analog of theorem C for rank 4 lattices as well. Okay, so this completes the genus 0 case, and yeah, then I said you do everything again for genus 1, and then you reduce the high genus case to 0 and 1. Okay, I don't think I have time to say a few words about theorem C, so I think I'm just going to stop there. Thank you.
Thanks a lot. Any questions, remarks?
Maybe you can explain in 3 words why theorem C holds.
Yeah, thank you. Wonderful. Okay, so basically you use 2 things. You use properties of Noether-Lefschetz loci and moduli, and you also use something that we call the marked point trick, which is a construction that in a family of stable curves allows you to mark points and then show that the locus where the curves are reducible is divisorial in the base. So how do you do this? So I take my special K3 X, I move it along a curve in the direction of such a general K3 of the same lattice. Maybe I can draw the picture. So I take a U inside M2D that contains my little point x that I want to prove that it contains a rational curve in L, primitive and ample. And then I move it in the direction of some y, where y is general of lattice lambda, of pic lambda. Okay, so theorem T applies here. Applies on y. Okay, so I have my curve here, and I want to deform it and show that it remains integral in x. So now, okay, if it remains integral, then I win. If it breaks, then it has to break into at least two irreducible components. So now what I do is I have an integral curve here, and by this RAN business that I mentioned earlier, I can cook up a family of stable genus zero curves on the entire over the entire surface U. So I might need to pass to a semi-stable reduction to make sure that I get a stable family. But essentially I get a family of genus zero curves mapping to every member of this surface. Okay? But I know that at one point, this curve has to be reducible. Okay, but now because of this business with the Mach point trick, which takes a bit of time to explain properly, which I'm maybe not going to do this right now, but in this family of stable curves, because there's one member which is reducible, there has to be a divisorial locus along which it's reducible. But then, so let me call this locus, I don't know, this some curve here along which the deformations of the curve from theorem T are reducible. But then if you choose the surface U very general inside the moduli space, this curve will be the only one where the lattice lambda persists. And if you do it this way, I mean, if the curve breaks up here, then those two curves, they have to span the whole lattice. So in particular, you show that this curve here has to be equal to this curve here, because along this curve, the lattice lambda persists. So here you use the fact that the Noether-Lefschetz locus, I mean, when you fix a lattice, the Noether-Lefschetz locus is really a divisor. So if I choose U generally enough, then I can make it so that there's only one curve, one irreducible curve along which lambda persists. But then if I know that these two curves are the same, I get a contradiction, because I know that here, the curve that I started with was irreducible, and along all of these it splits, so it had to be irreducible to begin with. Yeah, so that's the. But you have to mark points in the moduli space and map to M04 bar and use some tricks, because it's not clear that this curve exists in U. But that's it. Yeah, there's some technicalities. Yeah.
So, if there are no further questions, let's thank Frank again.